In this lesson, we're going to look at what's called the side splitter theorem. And it basically says if a line is parallel to one side of a triangle and intersects the other two sides, then it divides those two intersected sides proportionally. Now, we've seen this before when we talked about the mid-segment of a triangle. Only in this case, we are not connecting the midpoints. D and E are not the midpoints. The only thing that we do know is that DE is going to be parallel to BC. So BC and DE are parallel. So that's the side splitter theorem is true, and the converse is also true. If a segment divides proportionally two sides of a triangle, then the segment will be parallel to the third side. So by proportionally, it means this. I can take the ratios of these segments, and they will be equal. And we can split this up several different ways. So based on the fact that BC is parallel to DE, here are some of the ratios I can write. AD, the distance AD over DB, so that splits the left-hand side. That's supposed to be a DB. Let me fix that. The distance AD over DB is going to be equal to AE over EC. So the two sides are in proportion, the way they're split up. And you can't do this for everything, so you do have to be careful. I can do the entire side to a segment. So I can say AB, which is the entire side, over either segment, DB, if I choose the bottom, that's going to be equal to AC over EC. That works. And there's others that would also work. AD over AB would work, equals AE over AC, DE. The other one that we have to be careful of, though, is when we're talking about the parallel sides. So these we have to be careful. They only relate to the small triangle and the big triangle. So because these segments are not divided at all, we need to look at whole sides. So if you look at the small triangle ADE, it's going to be similar to triangle ABC. So if I'm going to set up a ratio with the bottom two sides, I can say things like this. The little side on the left over the entire thing, which is the big triangle, that's going to be equal to the little side on the right, which is AE over AC, and that's equal to DE over BC. That's the only time you can set this up, is when you use the top sections, the whole sides of triangles, not DB and EC. We cannot relate these two sides to anything on the parallel lines. So next we're going to work a few examples of this. Alright, here we have a standard setup. We have that DE is parallel to AC, so I'm going to put those markings in there. And in this example, we're dealing only with the sides. In fact, a lot of the things we're doing today, we're only dealing with the two sides. So we can set up just about any proportion, and that's going to work out for us. If we look here, we have the whole side AB, and then the top, and the whole side over here, and we're trying to find the top. So we don't have to do any subtracting or addition or anything like that. I know that AB over DB is going to be equal to CB over EB. And now I just substitute in. AB is 8, DB is 6, CB is 16, and EB is x. So you cross multiply, and you get 8x is equal to 96. And in this case, x is going to be equal to 12. That's the only thing I'm looking for, so I am done. In the second example, we have our segments this time. We don't have the whole sides, and we don't need them because the 2 is going to go with the x and the 8 is going to go with the 12. So I know that DB over AD has got to be the same proportion as EB over CE. So 2 over 8 is equal to x over 12, which gives you 8x is equal to 24. And x is 3. These are relatively easy to solve because cross-multiplying is something that most kids can do. Again, when you're dealing with the sides only and not the parallel lines, then you can use segments in your proportion. Alright, so this is a pretty short lesson today, and then we'll spend a lot of time in class practicing these things. Here we have a triangle, and this time I have the 15, the whole side to the lower segment. Again, we're assuming that the two bottom lines are parallel. So if you look at this, but up here I need BE and EC. There's a lot of different ways you could do this. What I would do, since I have a single X here, I would find the missing component there, which means BD is going to be 15 minus 6, which is going to be 9. That's going to be easier to do. And then you just set up your proportion. 9 over 6 is equal to x over 8, and 6x is going to be 72, and it looks like x is 12. That's not the only way you could have set this up, so think about how else you could do this using the whole side instead of subtracting. And we will look at that in class. So that's an introduction to the side splitter theorem. And we're going to be working more of these examples in class. The biggest thing is you have to remember we can use proportions of the sides that are split up, but we can't use the lower sides here when I'm dealing with the parallel lines.